Hi, my name is Joel Weinstein with Micromotion. Today I will discuss how entrained gas can affect the Coriolis mass flow meter. There are two main things to consider when working on an entrained gas application with a Coriolis meter. First, what does the meter actually measure? Second, what are the sources of errors? As with all meters, Coriolis meters are only capable of measuring what goes through them. If the process fluid is a mixture of liquid and gas, then we accurately measure all mixture properties. We measure mixture mass flow, mixture density, and mixture volume flow all properly. In applications involving liquid flows with small amounts of entrained gas, mass flow meters have an inherent advantage. Users typically want to know the liquid quantities, not the mixture quantities. In the case of mass flow measurement, the mixture mass flow, which we measure, is nearly identical to the liquid mass flow because the mass of the gas is negligible. The same is not true for density and volume flow. For example, if 2 barrels of oil and 1 barrel of air flow through a volumetric flow meter, the meter will simply measure 3 barrels, and thus will over-report the amount of oil. Now let's discuss the errors associated with entrained gas. The primary source of error from entrained gas in Coriolis mass flow meters is called decoupling. There are other sources of error such as compressibility, but decoupling is dominant. Decoupling happens when the fluid inside the tube doesn't move exactly with the flow tube. When that happens, errors occur, which are dependent on meter and fluid properties. In the case of single-phase flow, there is only liquid inside the tube, and the center of gravity, the green square, moves directly with the center of the fluid. So all is well and there is no error associated with decoupling. However, in the case of two-phase flow, the bubble can move separately from the liquid, which ultimately causes the center of gravity to move separately from the flow tube center of gravity. And in the case of high viscosity, because the viscosity grabs onto the bubble, there's very little motion of the actual bubble and therefore very little motion of the center of gravity. So we have very small errors. In the case, however, of two-phase flow with low viscosity, it turns out that the bubble can move further on each oscillation than it could when there was higher viscosity. And what this causes is even greater error inside the tubes because the fluid is moving separately from the tubes. In the case of high-frequency, low viscosity, you basically have a worst-case scenario. In this case, decoupling is the greatest, and the bubble moves further than it could in any other scenario. Therefore, the errors are the greatest. While Micromotion manufactures meters with a range of frequencies from low to high, our low-frequency Elite meters are recommended for applications involving entrained gas, as they are usable over a much larger range of gas volume fractions than a high-frequency meter. Aside from having a low vibration frequency, Micromotion meters improve immunity to entrained gas by employing a state-of-the-art transmitter with the latest in digital signal processing algorithms. This plot shows the performance of a Micromotion Elite Coriolis meter in a typical entrained gas application. The y-axis shows percent mass flow error, and the x-axis illustrates average gas volume fraction. Typical applications have less than 1 or 2% gas volume fraction. Laboratory data shows that for water at a flow rate of 250 pounds per minute, measurement performance of better than 1% is achieved with volume fractions of less than 5%. All flow meters have problems with entrained gas. For example, turbine meters can overspin and cause damage. All volumetric meters over-report by at least the amount of entrained gas. For example, a volumetric meter over-reports liquid quantities by 5% if 5% gas volume fraction exists in the pipeline. Elite Coriolis meters have the optimal geometries and state-of-the-art electronics to be able to mitigate errors caused by lower levels of entrained gas.